So back to special diodes again. Um, that one was getting to be close to 25 minutes, and I know it takes a while to download some of these, especially if you're on a slow link. I don't like to go any longer than that. This one's probably going to be shorter, though. I do want to talk about, I think I got three different ones here I want to look at. The first one, it's called a varactor diode. And notice it's got a double cross bar, so it looks like a capacitor on top of the diode, and that's exactly what it is. It is a voltage variable capacitor. That's what the function that it implements anyway. Notice I put a variable supply here. If I vary that supply, I change the voltage of the, or I change the capacitance of the diode. Now, all diodes have capacitance. All diodes have capacitance. In the other types of diodes that we're not making use of that capacitance, we call it a parasitic capacitance, like a parasite, something we want to get rid of. It slows the diode down from changing back and forth between forward and reverse bias. But in the varactor diode, we actually make use of that capacitance. We can we use a DC bias to control the amount of capacitance, and we can put maybe an inductor in parallel with that. Remember, inductor and capacitor together have a resonant frequency, and by varying that capacitance, we can vary that resonant frequency and then make that part of an amplifier circuit or an oscillator circuit, I should say, to produce different frequencies. And that's how we tune radios and tune cell phones and tune televisions nowadays. It's more complicated than that, but that is the heart of it, the varactor diode. So let me draw a little bit here. Remember my PN junctions we looked at earlier? In a previous video, I did that in 2 dimensions, but they're actually a 3-dimensional kind of thing, naturally. And do a very good job there. These should all line up. But that's close enough for what we're doing here. maybe. All right, this slice right here in the middle, right here, represents the junction. This is my P region on the left. This is my N region on the right. This is my depletion region. And this is my PN junction. Now a capacitor, see how I want to do this. Consists of two parallel conducting plates I'm not going to draw the hidden lines on this one. That looks good enough. Separated by an insulator. Now the plates have an area we'll call A. The separation is a distance we're going to call L. And then the insulator has a property we call the dielectric constant. We use the letter epsilon for that. And that's just a measure of how good of an insulator that is. Dielectric is just another word for insulator. And so the amount of capacitance that I have is equal to epsilon A over L. Well, in the case of my in the case of my varactor diode here, the area is the areas here. The interface between the P region and the depletion region and the N region and the depletion region. Those are my areas. Those are my conductors. P and N both conduct. They both have charge carriers. But the depletion region is an insulator. So this length of the depletion region is my L. And I use the same formula. Now, if I apply a voltage to that, remember these are plus charges and these are negative charges in the P region and the N region. If I put a reverse bias voltage there, and make that a variable, then I can, when I reverse bias the depletion region, remember the positive charges get attracted to the negative side of the battery, and the negative electrons get attracted to the positive side of the battery, and they cause the depletion region to get wider. The more I make this voltage here, a bigger V on the battery is going to make a wider depletion region, and a smaller V is going to make a narrower depletion region. So what I'm doing, in essence, is controlling the L in that equation. If I make the depletion region wider, which is a bigger voltage, I have a bigger L and a smaller capacitance. If I use a less voltage to make the depletion region narrower, I have a bigger L, or a smaller L rather, and a bigger capacitance. So that is the varactor diode story. Let's look at just a couple more. This is one you should already be familiar with. the LED, which of course stands for light. And it just looks like a common diode, but there's some arrows coming out representing rays of light. And we've used these for decades as little indicator lights on circuit boards and on computers and televisions and everything else. I mean, if you have a TV remote control, some of them use infrared light emitting diodes. Infrared means a shade of red of a low enough frequency your eyes can't see it, but it can be detected by other electronics. And if you have a remote control that has to be pointed at the TV without anything blocking in between, then that's probably an LED infrared. They can also use RF radio signals. So if you can just point the remote over here at the wall and the TV's over here to your right or something and it still works, and that's probably a radio frequency. But it can be either. Let's see, where did I hide my LED? Here we go. And this is just a basic circuit. I mean, if I have a vote, it could be a more complicated circuit, but this is the simple version of it. I notice I put a variable supply again here. You could really do it either way, have a variable supply or a variable resistor. And what the variance will do is control the current. Remember, a diode does not control the amount of current. It just determines whether it's forward or reverse, whether there's current or not. The resistance and the voltage then determine how much current. So the more current that I put through the diode, up to a point at least, the brighter it's going to shine. And the less current, the dimmer it's going to shine. And nowadays, in the past few years, they've started making light bulbs that are made from LEDs. I've got flashlights that are brighter than any flashlight I've ever had before that's made with LEDs, white LEDs. Now, they come in different colors, of course. They come in red and amber and green and blue and infrared, we already mentioned, and white, and there are probably others. And nowadays, modern TV sets, these flat screens, are mostly made of millions of different color LEDs, all put together in a grid behind the television screen. And there's like a matrix of electronics that every fraction of a second updates which ones are on of which color and which ones are off to give you a TV picture. So this is a very commonly used item. Now, it does have a corresponding counterpart, I guess we'd call it, called the photodiode. And it's just the opposite of the LED. Notice the rays of light are going in to the diode. So this type of diode, if you shine light on it, it'll produce a voltage and a current if it's in a complete circuit. We use these in solar cells. We also use it, the idea of the TV remote, if I'm using the infrared LED in my TV remote control, then in the TV itself, I've got a photodiode that senses that infrared and knows what button you push. There may be a photo transistor. Now, we also do have photo transistors. It could be either one. And the way it works, let's see. There you see the rays of light going into the diode. I'm not going to get it where I want it, I don't think. I didn't crop that one off very well. There it is. And again, I shine light on the diode, it produces a voltage. Actually, I think I got the diode upside down. I think it should be in the other direction. I'll have to double check that one. But anyway, either way, you shine light on the diode, it produces a voltage that supplies a current to the resistor. Now, we can combine the two of those together. And again, this is fairly commonly done. We already talked about having the remote and the TV, but sometimes those are put together in a single package. Now, this is called an optocoupler, or sometimes called an opto-isolator. Now, if I have a transformer, the primary is not electrically connected to the secondary. So whatever circuits I have here is electrically isolated from the circuits on that side. They're magnetically coupled, but electrically isolated. Well, here they're electrically isolated. Once again, this left side of the circuit from the right side, they're not connected electrically, but they are connected optically. The current going through the LED produces light, which is received by the photodiode, produces a voltage and current in the right side of the circuit. So this is a technique we use sometimes to, I guess one of the main uses for it is reducing noise. If I have a really noisy circuit here, that does block out some of the noise going through to the other side. And again, there's other reasons. I won't get into the details of all of it, could take all day. But anytime we want to electrically isolate two circuits but still have them talk to each other. Now this is one-way communication. Now you could have a second one going in the opposite direction. The LED on the left and the photodiode on the right. I'm going to draw it that way this time because I'm still not sure. Now that would communicate left to right. You just flip it over. So you could have, if you wanted two-way communication between circuits, you'd have to have two isolators like that. Anyway, that concludes my lectures on diodes. My next lecture will start us into transistors. And we're getting short on time, so watch for it. It's going to come out probably the next couple of days, probably tomorrow or Monday. But anyway, I will give you a little bit of homework based on this one, and that should be due, let's say, probably Tuesday. But I'll post it when I post it on Blackboard. I hope you're staying safe. Have a good day.